Okay, let's take a look at converting back and forth from exponential to log and log to exponential. This is some information that you probably are already familiar with. Hopefully you covered it in Algebra 2, but let's just review it. An exponential expression basically is an expression that has a base and then a number that's raised to a power, we call it, and that number is the exponent, and it tells us how many times we're going to multiply our base. So basically 3 times 3 equals 9, so 9 is the value of the expression. Okay. The log expression, we'll notice that it also has a base. Log base 3 of 9 equals 2. So my base is 3 and the value of my expression is 2. Notice that the 2 and the 9 have changed places. And when the x and the y switch like that, we call that an inverse. And so what we're going to eventually understand is that exponential expressions and logarithmic expressions are in fact inverses of each other. That leads to the expression, the general for exponential and logarithmics. If my base is greater than 0 but not equal to 1, log base b of x equals y, if and only if b to the y power equals x. So let's see if we can convert back and forth. For example, we're going to convert this logarithmic expression into an exponential expression. We're always going to start with the base. So I want you to make sure you remember to start with the base. Okay? And so this is the same thing as saying okay, I forgot my 2. Log base 3 of 9 equals 2. There's my full expression. So we're always going to start with our base, and I'm going to use this little what I call horseshoe technique here. 3 to the second power equals 9. And so my exponential expression, my base is the same, but now that I'm writing an exponential expression, 3 to the second power equals 9. Take a look at problem number 2. Again, we're going to start with our base. And I'm going to use my little horseshoe approach here. So 5 to the negative 1 power equals 1/5. So that would be my exponential expression that we could roughly say is equivalent to this logarithmic expression. What if we wanted to go the other way? What if I was given exponentials and I wanted to write logs? Same thing. I'm still going to start with my base. Okay. Do my little horseshoe here. So basically we're going to say log base 5 of 125 is equal to 3. Log base 5 of 125 equals 3. Over here, again, starting with our base, log base 6 of 1/6 is equal to negative 1. Log base 6 of 1/6 is equal to negative 1. Okay, so as you can see, this property holds true, how we're able to write back and forth. And it's good to be able to do that because that can help you figure out answers to problems. So how do we apply this information? Okay, well, take a look at number 5. We're asked to evaluate. Now one thing that you might want to do when you're evaluating, even though you don't see it here, is set it equal to x. Something else you don't see is there's no base there. Well, that's because if you're just given log, that's called a common log. And it's called a common log because it's log base 10. So there is a base. We just don't write it all the time if it's base 10. There's also another type of log. It's called a natural log. And if you look on your calculators, you'll see ln. ln comes up more frequently in physics and biology and other applications with formulas because the natural log is basically the inverse of the natural exponential. So it has a base of 2.71. So if I write the 10 in here, because that's what the common log is, I end up with, starting with my base again, 10 to the x power equals 100. Now notice my bases aren't equal, so I can rewrite this now as 10 squared, so x is going to equal 2. Log base 3 of 27. Once again, if I put that equal to x, and convert this to an exponential. Now, why am I converting to an exponential? Because I'm much more familiar with exponents than I am with logs. So since I can rewrite it, it's just easier to deal with the situation, deal with the problem. 27 can be written as 3 to the third power, so x is going to equal 3. Okay, moving right along to number 7, log base 4 of 1/16. Well, again, if I set it equal to x, I'm going to end up with 4 to the x power equals 1/16. Now, I do have to do a little bit of thinking here, so let me get my cloud out. 4 squared is equal to 16, but that's not 1/16. So how do I get that 16 in the denominator? Well, I make it a negative exponent. Okay? So therefore, 4 to the x power is equal to 4 to the negative 2 power, so x is equal to negative 2. A very simple problem over here, log base 2 of 64. Again, if I set it equal to x, I end up with 2 to the x power is equal to 64. So 64 is 2 to the 6th power, so x equals 6. Now what about solving an equation? Could I use this to help me solve an equation? Now this isn't the only way to do this, but this is one thing that you could use, and that's to rewrite this into an exponential expression. With my log base 3, I end up with 3 squared is equal to x minus 4. 3 squared is 9. Add the 4 now, and we end up with 13 is equal to x. So using what we know, converting logs to exponentials, we can solve equations. And my last problem here, again, I don't see a base, so I'm going to assume that it's 10, a common base. So I'm going to end up with 10 to the third power is equal to x plus 3. Again, if I circle my base, do my horseshoe, there it is. And so 10 to the third power is 1,000. Subtract 3, I get 997 equals to x. So converting back and forth from exponential to logs is a very powerful tool. It allows you to evaluate, to convert, and to even solve equations. Remember, it's all about the base. You always start with the base when you want to convert from a log, and you start with the base when you want to convert with an exponential.